All right, so part 3 of section 4.3 has to do with finding absolute maxima and minima, together called absolute extrema. All right, so as an example, I want you to look at this function. Y is equal to x squared. So this is your, basic parabola, except the domain has been restricted to the closed interval from -1 to +2. So it's this part of the parabola. And you can tell just by looking at the graph what the absolute maximum is and what the absolute minimum is. What is the absolute maximum? That would be the highest or the largest y value seen here. And of course, that's 4, right? And that happens when x is equal to 2. That happens to be the right endpoint. Okay, it is an endpoint. The absolute minimum is not at the other endpoint, by the way, because the other endpoint is -1, 1, and there is definitely a point that is lower than that point on the graph, which is 0, right? 0 seems to be the lowest value of y, the least value of y, and therefore the absolute minimum is 0 at x is equal to 0. Now that actually happens at the critical point of the graph, because as you can see, y prime is 2x, and the only critical point is when this is equal to 0, because this is always defined. Remember, this is a differentiable function. And so this is 0 at only when x is equal to 0. So this happens at the only critical point of the function. So it looks like these are the candidates that needs to be considered when you are looking for absolute extrema, right? And in fact, that is the that is the theorem that I'm about to state. Okay, and that is the absolute maximum and minimum together. They're called absolute extrema of f on a closed interval a b must occur or happen at critical points or endpoints, one of the endpoints, A or B. Okay, so those are the only places that you need to take a look at before you decide what the highest, largest value is, which is the absolute maximum, and what the lowest value is, the least value, which is the absolute minimum. And once you find these, then you know where they occur. All right, so how do you find where these things are going to happen? Okay, so here's a simple guideline, and this is something that is easily understood, having understood this theorem. Okay, so number one, find all critical points. Find all critical points of f. Now, of course, you want to exclude anything that's not on this interval, right, a, b. So if if this is -1 to 2, and if one of the critical points is 7, for instance, you don't have to worry about them, right? So evaluate f at all critical points. So if you find 3 critical points in the interval a, b, then evaluate the function at all 3 of them. And then you evaluate f at the endpoints, a and b. Okay, now you have all the candidates where, absolute maximum has to occur and where the absolute minimum has to occur. And therefore, the largest fx value, the y value, is the absolute maximum, obviously, and the least is the absolute minimum. So that sounds pretty easy, okay? And you say, well, that's it? Yeah, that's actually it, okay? Now, you still don't know what the graph looks like, but these are the all the possible places where the absolute maximum and the absolute minimum could occur. And so you have, you have basically searched every possible place, and you evaluate and compare among those finite values, and that's all you have to do. All right, so let's go ahead and apply this for the parabola that we have just considered from -1 to 2. F prime is 2x, which is 0 only at x is equal to 0. So this is the only critical point. right? So f0 is 0. F negative 1 is negative 1 quantity squared, which is 1. F of 2 is 2 squared, which is 4. That is the highest, the largest. So this is the absolute maximum value of this function on this interval. And this is the absolute minimum value occurring at 0. Right, as we predicted. And of course, we knew the answer from the graph. That was obvious, but you can see that this procedure works, right? All right, finally, this is our last example of this section. F is x squared minus 3x to the 2/3. So this part makes it slightly more complicated. And let's say this is we are going to look for its absolute maximum and absolute minimum. And we'll find out where those values occur on the interval from 0 to 2, including 0 and 2. All right, by the way, how do I know that I can find the absolute maximum and the minimum? Is there any guarantee that there will be an absolute max and absolute min? And the answer is yes, this is a continuous function on 0 to 2. And because it's continuous on a closed and bounded interval, there will be a maximum value, absolute maximum, and there will be an absolute minimum value, okay? We are guaranteed that by the extreme value theorem. So let's take the derivative, okay? We'll find what I call the usual suspects, okay? What are the usual suspects that you are supposed to round? You know, you're supposed to round up the usual suspects, and that's all the critical points and the endpoints, because every max, well, you know, both max and the min, absolute max and absolute min, have to occur at a critical point or the endpoints. All right. So the first thing is to find the derivative, which is negative. Okay. So this is 2x minus 3 times 2/3 times x to the new exponent, which is 1 less than 2/3. All right. So this is 2x minus, well, let's write 2 divided by x to the 3rd power, which is the cube. And you can factor out 2. It's x minus 1 over x to the 1/3. All right, now, there are 2 types of critical points, right? So you know that f prime does not exist. If you can find one of those places, or if you can find a point where the derivative is not defined, then that's a critical point. And there is one such point, where x is equal to 0, because that will give you the 0 denominator. Now, is this 0 a part of the interval? Yeah, it is actually the end point, the lower end point, right? It is in the interval, so let's include that. All right, that's something that you have to watch out for. I mean, 0 is a critical point. There's another critical point, and that's when this is equal to 0. Now, when does that happen? Well, 2 is never equal to 0. X and x to the 3rd can be equal to each other. Now, this is, whoops, what did I just say? No, yeah, that's true. This is what I want to prove. I want to find, right? So x to the 4/3 is equal to 1. What's the solution here? I think there are 2 solutions. X could be actually positive 1 or negative 1. Okay, because negative 1 cubed is negative 1, its 4th power is 1. However, this is negative 1 is not in this interval, so we can cross this out. We don't even have to worry about that. That's a usual suspect outside of the domain, so that's not a suspect at all. All right, so we have 1 and 0, and we have an endpoint, right? So let's find out f of 0. That will be 0 squared minus 3 times 0. That's 0. And by the way, this is an endpoint already. Also a critical point, just by the virtue of the fact that the derivative is not defined at 0. When x is equal to 1, you have 2 times 1 minus 3 times 1 to the 2/3, which is 2 minus 3, and that's negative 1. Okay, that is the only critical value that is not an endpoint. Okay, and finally, 2 is the other endpoint, right? So let's plug in 2. What is the function? 2 squared minus 3 times 2 to the 2/3. What is that? I don't know. It's a cube root of 2 squared, right? So for this one, you would need a calculator. And if you take your calculator and evaluate this, okay, so you would do 4 minus 3 times 2 raised to the power of, and then parentheses 2 divided by 3, you will get negative 0.7622, blah, blah, blah. Okay, that is an endpoint. And these are the only points where f can have its absolute maximum and absolute minimum on this interval. Now, which one is the largest value? 0, -1, -0.7. This looks like the absolute maximum because it's the highest point, even though it's 0. And this is the absolute minimum. Okay, so you can say f on this interval has its absolute maximum, which is 0, occurring at 0, and its absolute minimum is -1, occurring at 1. And by the way, at this point, you still don't know what the graph of this looks like, but if you are to take your graphing calculator, speaking of graphing calculator, how would you program this on your calculator? You know, y is equal to is the prompt you'll be given. I would say x raised to the 2 power, second power, minus 3 times x raised to, and I would use the parentheses 2 divided by 3, close parentheses, okay? And you enter this to graph this function, right? And of course, you would just wanna just take a look at only the portion corresponding to 0 to 2. Anyway, you do that, and then you get this graph, 0, 0, 1, -2, and when x is 2, you get this value here. Clearly, this is the absolute maximum, and this is the absolute minimum, okay? Just as our calculation showed us. So you can see, I hope, that calculus, differential calculus, actually gives us a very nice way to find the maximum and minimum points of functions, whether you're talking about absolute values, absolute max min, or local max min. All right, and so make sure you get this because this is one of the most important applications of calculus. Optimization problems have to do with finding the maximum or minimum, you know, like what's the maximum profit or what's the minimum cost. Those are called optimization problems, which we will be seeing shortly in chapter 4. Okay, so this concludes chapter 4, section 3. And in the next section, we will do very theoretical work. Section 4.4 is about different theorems leading to some great conclusions and applications of the derivative. I will see you then.